Physics plays a very important role in the understanding of baseball. We're going to concentrate on two aspects of baseball in relationship to physics. First, we're going to look at the behavior of a pitched ball, and the second lecture will be devoted to a batted ball and the bat-ball collision. We need to start with Sir Isaac Newton, and Newton came up with his three laws that are the foundation of much of physics. We'll review these in the second lecture, but we can briefly talk about them now. Newton's first law is that a body in motion will continue in that trajectory until some force acts upon it. The second Newtonian law is a very simple equation, F equals ma, and it just describes the relationship between the mass of an object, its acceleration, and the force that results from the interaction of the mass and acceleration. So F equals ma is that equation. And the third Newtonian law is that for every action, there is an equal and opposite reaction. This law is sometimes referred to as the law of conservation of energy. So from a physics point of view, we can talk about various behaviors and postures that a pitcher goes through to deliver a pitch with the maximum velocity. So as you can see, there are three cocking movements and three launching movements. So a cocking movement is going to essentially store energy that can be released to throw the ball forward, and the launching movement is when the ball is actually moved in a forward direction. So we can see that there's the stride, and then you can have a trunk and shoulder rotation, and you can have flexion of the trunk. So all of those are going to be driving the ball forward. We have this forward arm rotation where the elbow and arm is cocked, and you drive it forward with great force to release the ball with considerable velocity. The elbow can be cocked as well and then extended. And finally, we have the wrists and fingers, which can be cocked and then driven forward to propel the pitch. So if we take a look at these different behaviors, you can see that early in the pitch, when the stride first starts, that the trunk flexion and the trunk shoulder rotation are most important, and they take up a fair amount of time, relatively speaking. Forward arm rotation only follows the trunk and trunk shoulder rotation, and the wrist finger flexion is the last behavior that's going to happen. So that's when the ball is going to be finally released from the pitcher's hand and travel toward the plate. We need now to talk about the Magnus force. So the Magnus force can be applied to any sort of solid object that is moving through a fluid medium. In this case, the fluid medium happens to be air, but liquids are also fluid media. Anytime you have a round ball like a baseball moving through the air, it has right around its surface a layer of non-moving air called the boundary layer. So the boundary layer is essentially annealed, if you will, to the baseball. It's essentially a small skin. So if you had a really small insect like a flea or an aphid or something like that, it could actually ride on top of the baseball within the boundary layer and not be flicked off as the ball is thrown. Now, the boundary layer is very important in interacting with fluids that are moving across the surface of a particular solid. What we have here is a ball that is obviously rotating, so it's rotating in a clockwise direction. And if you think about what is happening at the lower part of the baseball, right down here, we've got the boundary layer stuck right onto the baseball. And then what the boundary layer is going to do is to push air just above it in the direction opposite the direction that the fluid is flowing across the baseball. So if this baseball is being hurled from right to left, it's going to be resisted by air that is passing across, that is indicated in the left to right trajectories here. So we see the baseball is going in one direction and it's encountering opposition in the opposite direction from the air that it's moving across. So what's happening here is the boundary layer is throwing air in opposition, in opposite direction to the air that's moving underneath the baseball. But let's look at what happens up above. Here we have the boundary layer, and it's going to be pushing air in the same direction that air is moving across the top of the baseball. So in this case, the boundary layer is pushing air in the same direction that this air resisting the baseball is flowing across the top of it. So what we have then is a situation down below where we have the boundary layer forced air is interacting with the air that's moving from left to right. As a result, the velocity of air is going to be diminished here. And what that is going to do is to increase the pressure. So the pressure, the amount of air beneath the baseball, is going to be relatively high because of this interaction between the air impelled from right to left by the boundary layer and the movement of air from left to right as the baseball passes to the left. Up above, we get just the opposite pattern, that the air moved by the boundary layer impelled by the curve of the baseball when it was thrown, is acting in concert with the air moving across the top of the baseball. So the velocity of air here is going to be relatively high. And that means that the air pressure here is going to be relatively low. So the spinning baseball has set up a pressure gradient. We have high pressure here and we have low pressure here. And what's going to happen is we're going to see a net movement upward. And that is called the Magnus force. Now, we want to be careful to realize that the Magnus force is independent of gravity. It has nothing to do with gravity. That if the baseball were spinning from side to side, we would generate a Magnus force that was parallel to the Earth's surface, not perpendicular to the Earth's surface. And we'll take a look at how that happens in a bit. And just to continue with a little bit of fluid dynamics, what happens when you get what is called laminar flow that is not turbulent, hitting a baseball, then it flows across the top and bottom of the baseball fairly smoothly. But once it gets to the back of the baseball, then these laminar flow lines break down and you get turbulence. So that's what these irregular eddies here represent. That's turbulent flow that happens on the backside of a baseball. Here's an example of the Magnus force on a spinning baseball versus a non-spinning baseball. So here the baseball is being thrown in this direction, leftward direction. It's being opposed by air moving that it has to move through in the opposite direction. And because there is no movement of the baseball, it's not spinning, we don't generate a Magnus force. In this case, the baseball is rotating in a counterclockwise fashion, so in fact it would be a top spin. So what we would have is the high pressure area would be on top of the baseball and the low pressure area would be on the bottom of the baseball. So in this case, the Magnus force is going from this direction down to this direction. So the ball would in fact drop as it goes through the air to a much greater degree than it would drop simply because of the effect of gravity. Let's take a look at an interesting video that was filmed from a dam, this time using a basketball.
Physics in action can sometimes be amazing, as these guys from the trick basketball team How Ridiculous show us. First, they go to the top of Tasmania's Gordon Dam, 415 feet in the air, and drop a basketball, no backspin. You can see it's pushed around by the breeze a bit, but pretty much falls right below where it was dropped. They do it again, this time with a backspin. Watch how far it goes! What happened? It's called the Magnus effect. Air on one side of the ball is going in the same direction as the spin and is deflected behind the ball. Air on the other side is moving opposite the spin. So, the air spinning with the ball applies an opposite, pushing the ball forward. Science aside, the real reason they did this was to set a world record for highest basketball shot, which they did, no doubt thanks to the Magnus effect.
Let's look at different kinds of pitches and how the Magnus effect influences their movement. So here we have a fastball, and a fastball is typically thrown with backspin. And the rotation, as you can see, is fairly high, 1,500 revolutions per minute. So if we're throwing a pitch with backspin, what that's going to do is to generate an upward Magnus effect. So it should cause the baseball to move upward, you would think. But in fact, to get the baseball to rise above the level at which it was released, you need to have a ridiculous RPM. It would need to be at least 10,000 RPMs to actually have the ball rise enough due to the Magnus effect to actually have it end up higher than the point at which it was thrown. A curveball, the ball is going to be rotated with topspin. And sometimes pitchers throw a 612 curveball, in which case the rotation would be exactly perpendicular to the surface of the earth. In other cases, they have a bit of an angle. That's, of course, shown here. The rotation is still pretty high, 1,500 RPM, but the speed is lower. A slider is thrown with rotation that is pretty much horizontal, thrown faster than a curveball, but not as fast as a fastball, but the rotation rate is somewhat less. And the curveball is going to break a whole lot more than a slider. And then a screwball is thrown with an opposite rotation to the curveball. So for a right-handed pitcher throwing a screwball, the ball would curve, as the pitcher watches it, the ball would curve from left to right. So from the perspective of a batter, a screwball appears to have the same sort of curve that a curveball from a left-handed pitcher would throw. There are two kinds of fastballs that pitchers throw. There's the so-called four-seam fastball, which you can see on the right, and the two-seam fastball. And it turns out that they differ in their behavior. The effect of the seams of a baseball is actually to increase the size of the boundary layer. So the thickness of the boundary layer is increased a bit by the stitches, the 108 stitches on a baseball. So that means that the effect of the boundary layer in pushing air as the ball rotates is going to be greater if you have balls with stitches as opposed to a sphere that doesn't have any stitches on it whatsoever. It turns out that a four-seam fastball interacts with the air in a uniform manner. So a four-seam fastball is going to show a Magnus effect, but it's going to pretty much go straight. So the fastball is going to come in, and it will, of course, drop some over the course of its flight, but it will not tend to dart left or right. That is the case with a two-seam fastball. With a two-seam fastball, we no longer have this symmetric movement of air across the seams. So one of the seams is going to be influencing the boundary layer movement of air more than the other. And so the result is that a two-seam fastball is typically going to have a little bit of left to right or right to left movement, depending upon how the pitcher holds it. So a two-seam fastball would be a fastball that has a little curve to it, whereas a four-seam fastball tends to be a rather straight fastball. Scuffing a baseball can cause it to do odd things, to take sudden movements. And if you have a scuff ball, the way to throw it is to put the scuff off to one side or the other. And that will cause it to interact with the boundary layer and with the Magnus effect to produce erratic flights of the baseball to confuse the batter. Let's take a look at this view from above of a curveball. And so the curveball is starting at the pitcher's mound at the 0 mark, and it's going the 60 feet 6 inches to home plate. And you can see above the time that is required to get there is shown 500 milliseconds or so. What I want to point out here is that the curveball follows the laws of physics, that the curveball is going to define a parabola, and this parabola is going to be followed because of Newton's first law. So you have an object in motion, it's going to continue in that motion until some other external force acts upon it. So it's going to smoothly curve. It's going to curve in a path that can be described by a simple parabola. You can see here halfway to the pitcher's plate, the sagitta, this point halfway between the release point and the pitcher's plate, that the ball has curved about 3.5 inches. By the time it gets to the plate, it's curved about 14 inches. But it's all because of the slow and consistent curving that happens along the length of the trajectory of that curveball. Baseball announcers and coaches are often unaware of the laws of physics. So you'll often hear about a pitcher who has late break on his curveball, or the fastball explodes at the very last minute. Well, that's all an illusion. So because no curveball is going to suddenly break when it reaches the batter, and no fastball is going to suddenly accelerate when it reaches the plate. It's all perception. And one reason curveballs seem to break right at the last minute is because of the behavior of the batter. So the batter will tend to watch the incoming pitch with his central vision, but then as the pitch starts to come, switches to peripheral vision, and then as the pitch actually gets to the plate, switching back to more centralized vision. And that result causes the baseball to appear like it's jumping in a most amazing fashion, like it's breaking really hard. But in fact, it is breaking perfectly normally, just according to the principles of physics. The batter thinks that it's breaking very quickly right at the end, but in fact, it's not that case at all. If we look down below, we can see the trajectory of a knuckleball. And with a knuckleball, the Magnus effect is not in play because the knuckleball doesn't spin. So the Magnus effect plays no role at all in the movement of a knuckleball. Rather, a knuckleball is going to be influenced by the turbulent eddies that are just in the air between home plate and the pitcher's mound. So a knuckleball pitcher, of course, has no idea where a particular pitch is going to go, and oftentimes they are truly bewildering, and sometimes they don't move very much and they get hit for home runs. And here we're going to look at a fastball, or two fastballs that have been thrown, and you can see that by the time they get to the strike zone, less than half a second has gone by. But you can see the difference between a 90-mile-an-hour fastball and a 93-mile-per-hour fastball. That the 90-mile-per-hour fastball, because it's in the air for a longer period of time, is going to be subject to the force of gravity, and it's going to come in a little bit lower than the ball that's thrown at 93 miles an hour. So the other thing we want to point out is that, as alluded to earlier, that even if you throw a pitch with lots of backspin, it's still not going to rise that much. There will be a little bit of upward lift created, but that's not enough to overcome the effect of gravity. So any pitched ball is going to end up lower than it was when it left the pitcher's hand. And the last item I want to talk about here in the case of pitching is the split-fingered fastball. There are actually two kinds of split-fingered fastballs. Some people pitch the split-fingered fastball, which actually has some backspin, but the backspin is not anywhere near as strong as the backspin of a fastball. And therefore, since it's not creating as much lift through the Magnus effect, it seems to drop much more than a regular fastball. So it comes in like a fastball, but it doesn't have the lift that a normal four-seam fastball would have, and it seems to drop. And the batter, of course, thinks that the bottom dropped out of it, but it's just because there's not as much upward lift created by the Magnus effect. And some split-fingered fastballs actually have topspin, and those are really effective because the Magnus effect there would be creating a downward movement, which would be augmented by the effect of gravity, and so those pitches are going to move down quite a bit. So the Magnus effect is an enormously powerful explanation of how pitch balls are going to move depending upon the grip and the rotation that the pitcher puts on the fastball to try to deceive the batters.